We know that the evolution of a quantum system follows the Schrödinger equation, and therefore all the information of the timescales of the system must be contained in the Hamiltonian, which is the energy observable. Furthermore, we've solved the Schrödinger equation, and we know that the energy eigenstates simply rotate. Their phase rotates according to the energy eigenvalues. So if you take those energy eigenvalues and divide by h bar, that gives you the corresponding frequency. Invert that, you get the timescale. That's the timescale of the evolution. But the energy is not uniquely defined. The only thing that's uniquely defined is the relative energies. We don't know whether zero in our energy is, but the spacing in the energies has to be physically defined. And so it must be those energy differences that define our key timescale. And this leads us to a universal physical tip, really. Always look for the fundamental length scales, time scales, energy scales, whatever, of your physical system. And without a single quantitative calculation, you can estimate what's going to happen to that system's behavior just from those scales and guessing what happens in the various limits. And calculations are usually just for getting the details of the curves in between. So let's come back to quantum mechanics once more. We have our fundamental three postulates that everything's described by a Hilbert space, that those elements evolve according to the Schrödinger's equation, except when we measure them, when they suddenly jump to eigenstates of our observables. We looked at the linear evolution, and we saw that it was described by a unitary operator. We saw that we could change our evolution. Instead of being associated with states, we could associate it with operators or some mixture. We looked at unitary operators defining transformations, and in fact unitary operators that depend on some parameter being continuous transformations. And then we saw Noether's theorem coming back. So we saw that symmetries of the Hamiltonian gave us conserved quantities, i.e. the generators of those symmetries. We saw that momentum was defined actually as the generator of translations, and similarly angular momentum is defined as the generator of rotations. We learned the Einstein summation notation. We learned that since angular momentum is the generator of rotations, it must follow these commutation relations. We saw that there are more than one kind of angular momentum. Orbital angular momentum is a form of angular momentum for spatially distributed waves. It's the old form, so L is R cross P, except now everything is operators, and that has the same commutation relations that any angular momentum must have. And we also learned that there's another kind of angular momentum that certain particles have, which is a finite dimensional form called spin. It's a kind of intrinsic angular momentum, and the spin operators in the x, y, and z direction also have to obey these commutation relations. And we saw the example of spin based on the Pauli matrices for spin half particles, such as an electron. Particles that have spin tend also to have orbital angular momentum in practice, of course, because they are distributed spatially as well. And particles that have both orbital angular momentum and spin angular momentum, the total angular momentum is just the sum of those two kinds of angular momentum. And the Hilbert space, instead of being described by a wave function throughout space, is described by a multi-component wave function throughout space. And so for a spin half particle, where there are two spin degrees of freedom, a spin up and spin down in any axis, then we have a two-component wave function over all space. For a larger spin system, then we can have more components, but there's always 2s plus 1 components of spin. Now you might be surprised that Lagrangians were so fundamental to classical mechanics, but quantum mechanics is all formulated in terms of the Hamiltonian. And if so, you're in very good company. Richard Feynman had a tendency to do almost everything his own way, and so perhaps it was no surprise that almost 2 decades after quantum mechanics was first invented, he went back and reformulated it in terms of Lagrangian mechanics. And this had 3 main success stories. The first was it led on to a strong development in quantum field theory and relativistic quantum mechanics, which is basically the deepest truth we know about the Hilbert space that describes all matter and energy today. The second is it's fundamental to the key calculation in particle physics. The key methods are based on the Lagrangian formulation. And thirdly, it's a very powerful way to look at the correspondence principle, the way that the classical world comes out of the large limit of quantum mechanics. Now classically, an object has a position and a momentum. Now by contrast, in quantum mechanics, a particle has all positions and all momenta at the same time. Classically, this particle follows the path of least action. So if it starts here and it's going to end up here, so if it starts at position A, ends up at position B, then there are many possible paths it could take to get there, and takes the one that defines the least action, where the action, remember, is just defined as the integral over the Lagrangian. So quantum mechanically, of course, you're never truly at positions A or B, or following any position in between, and so therefore the idea of a path doesn't really make sense. And the idea of the Lagrangian formulation, as described by Feynman, was that a particle takes all possible paths from A to B. And we're going to show that the path integral formulation of quantum mechanics is equivalent to the Hamiltonian method that we've already learned by showing that they both produce the same unitary evolution operator. And we're going to do that in the position basis. So to put this in the position basis, we can multiply by 1 always. Remember the completeness relation. And so if we apply this operator to here, we'll get, and we apply it both at the start and in the middle here, and remember to use a different dummy index for the two, so I'll use x and y. Now we're going to call these objects here the wave function, because notice this is just a complex number to put the state into the position basis, and so that's what we call the wave function. And I'll use phi as my wave function. Same here, this is the wave function at position y and time t0. And here, this object here, I'm going to call, that's again just a number, but it's a function of x, t, y, and t0. And this is true, so we've got a superposition of basis vectors here and a superposition of basis vectors there. And so each of the components must be the same. And what we've done here is we've got an equation equating the coefficients. This is the wave function at some position x and later time t, is some linear combination of the wave function at earlier times and at different positions. And this set of coefficients here, this arbitrary linear operator, is known as the propagator. And it's defined simply as the time evolution operator in the position basis. And you can see it takes us from position y at an early time t0 up to position x at a later time t. And that's why it's called the propagator. And the propagator is often called a Green's function as well, hence the g. Now there are two main methods of finding it. The first is the method you know, the Hamiltonian method. And that is to remember that we know how this time evolution operator is calculated. And therefore we simply solve that and take the inner product with x and y, and we get the propagator. The second is called the path integral method. And in this case, we take 3 steps. First, we find all the paths joining the 2 points. The second is we calculate the action for each of those paths. And the third is we add them all up in the following way. And so this a here is just a normalization constant. We have to take the sum over all paths, and we take the action, and that's just the phase of the path. So every path counts equally. So there's no small paths and big paths. They're all equal weighted, but their phases change according to the action of the path. And it turns out that when you add them all up like that way, you actually get the correct version of the propagator. And in practice, showing this equivalence is really quite involved, and it's going to take us a little time. And indeed, this idea of summing over all the paths in a quantitative sense is a new idea, and we have yet to define what it means. And in practice, we'll do that as we go through the proof itself. But first, let's check that we can actually calculate the action for different paths. So let's start with a specific example. In one dimension, we'll have a potential that's quadratic, so it's a harmonic oscillator. And let's assume we start at the origin and we go in a straight line at a constant velocity. It has to be a straight line because it's one dimension, but constant velocity is our assumption. Now calculate the action if we're going from the origin to a point following this path.